Okay, so we are looking at the second method of balancing redox reactions. So this is called the half-reaction method. So it's very similar. You should get the same answer regardless of what technique you use for balancing. I would suggest you should know how to balance each method, okay? But normally, if we were having an exam, or if we were having an exam, I would say on the exam you can have your choice of what method you'd like to use. However, let's say you're doing a quiz or a test. Typically, I will be specific in the type of method that you will need to use. Okay, so we're looking at half reactions here. So the main difference is actually the setup at the beginning of your reaction. So we're still going to go through and assign oxidation numbers, but the difference is instead of beginning to balance it right away, what we would first do after assigning oxidation numbers is write out the two half reactions. Okay, so essentially you'd have your oxidation half reaction, you would have your reduction half reaction, and then what happens is you would balance each of them separately, and then at the very end you would recombine them to get your total redox reaction. So it's going to be the same method. So we have to make sure the number of electrons lost is equal to the number of electrons gained. We're still going to follow the same steps, right? So first you would balance the item that is either oxidizing or reducing. Then you would look at other elements. Then you would look at oxygen, and then you would look at hydrogens. Okay, so and then if it's acidic or basic, you're going to see the same conditions that we looked at in the last lesson. Okay, the main difference is you're balancing them in their half reactions instead of in the total reaction. Okay, so as I mentioned, the steps are the same here. So you're going to write out the oxidation and reduction half reactions, including the electrons in your half reaction. You're going to balance the number of atoms other than hydrogen and oxygen. And then oxygen atoms we're going to balance by adding in water molecules, hydrogen atoms by adding hydrogen ions. And then, of course, if we have acidic or basic solution, that will come in later. What you then do before re-adding your two half reactions together is you have to make sure the number of electrons lost is equal to the number gained. So we may have to multiply the half reaction by a factor in order for that to happen. Once that's done, you add the two half reactions, and of course you would cancel out whatever you can from either side or combine like terms. Similar to when we added in the different steps of a Hess's law. Same thing, we're going to combine like terms, cancel whatever we can, and then rewrite out our final equation. So let's take a look at an example here. So of course, learning the steps is easier to see when you're looking at an example. So first thing, we're going to assign oxidation numbers. So same procedure as always. So oxygen is -2, so meaning my oxygens here is -14, which means I need +12. So each chromium is a 6. Here I have, remember that nitrite is a polyatomic ion. So here I have -2 for my oxygen. My hydrogen is, my nitrogen is +3, right? To get that equal to, so we have -4, so it has to be -1 overall. And then hydrogen, of course, is +1. Here we have a chromium ion. It's a simple ion. The ion is there. Oxygen is -2. And then, of course, this nitrogen is going to be a +5 because we need the -6 and +5 to give us an overall -1. Okay, so let's identify what is happening first. And, of course, we're doing an acidic example first so we can see what it would look like. And then, of course, we'll do an example looking at a basic solution as well. So chromium, we can see right away, is going from +6 to +3. So what's happening here is we have a gain of 3 electrons, which means this is going to be our reduction half reaction, right? Hydrogen's not changing, nitrogen is changing. So nitrogen is going from +3 to +5, which means each nitrogen is losing 2 electrons. And that is our oxidation half reaction. Okay, so we're going to look at each reaction itself, like balancing them separately. Now, it's important when you're writing a half reaction and something is with other elements, you have to keep them together. So let's take a look at we'll do our oxidation half reaction first. Okay, so nitrogen is the actual element that is doing the change. But we can't forget the different things that nitrogen is with in this molecule. So on the reactant side, we're going to have HNO2, and the product side is going to be 2 electrons, of course, because they're losing 2 electrons, plus NO3. So again, same thing. We cannot just write the nitrogen in. We have to write the entire species that the nitrogen is a part of. Okay, so the first thing we would want to do is balance out the item that is actually oxidizing in this case. So we have 1 nitrogen, so we're good there. We're then going to look at any other elements other than oxygen and hydrogen. We have none. So now let's look at our oxygens. We have 2 on the left, 3 on the right. So that means we need 1 more oxygen on the reactant side. So now we have 1, 2, 3, 1, 2, 3. So remember, you don't just add in oxygen, you're adding in water molecules. And let's look at our hydrogens now. So we have 3 hydrogens on the left side, no hydrogens on the right-hand side. So we would add in 3 hydrogen ions to the right-hand side. So actually, this half reaction is now fully balanced. So let's take a look at the reduction half reaction. So this is where we're going to now have our dichromate becoming chromium ions. Okay, so we have our reduction half reaction. So we're going to have our dichromate. I'm just going to rewrite this out here. -2. And in this case, let's take a look at, I'll go back to look at the electron count in a second. Okay, so chromium is going from +6 to +3. So each one of those chromiums has to gain 3 electrons. So remember, whenever you're looking at half reactions, you have to consider the total number of electrons that are being gained or lost. So in this case, each one is gaining 3, but there are 2 of them. So when we write in our electrons here, we have to consider that there has to be a total of 6 being gained. And right off the bat, we know the first thing we need to do is balance out that chromium, because that's the actual substance that is being reduced. You can't have 2 chromium on this side and then one of them disappear and be left with only 1, right? So you must balance that portion first. Okay, so then we would look for other elements other than oxygen and hydrogen. So we don't have any other ones, but we do have oxygens. So because we have 7 oxygens, we need to add 7 waters to the right-hand side, right? So we have 7 oxygen, 7 oxygen. And now we're going to look at our hydrogen ions. So we have no hydrogen on the left. We have 14 on the right now. So we need to add in our 14 hydrogen ions. One of these is a plus and one of these is a charge. Okay. 14 hydrogen ions on the left. So now we have a fully balanced reduction half reaction. Okay. And actually, just to make this easier, I'm going to write the oxidation half here so we can compare the two when we're ready to go. So we had a water, we had HNO2, we had NO3, and we had 2 electrons gained, and we had 3 hydrogens that were added. Okay, so at this point, we're at the step where we have both half reactions fully balanced, like we balance them individually. So we want to eventually add these 2 together to get an overall redox reaction that's balanced. Now, this is where you're going to stop and look to see how are the electrons. So in this case, our reduction half reaction is showing 6 electrons being gained, but our oxidation half reaction is showing only 2 being lost. So before we add these 2 half reactions together, we have to make sure the same number of electrons is lost and gained. So meaning we are going to have to multiply this second reaction, or I should say the oxidation reaction, by a factor to make it equal to the 6. So in this case, we're going to multiply by a factor of 3. So now this would apply to everything here, just like it would if you were doing Hess's law. So that means we would now have 3 waters, 3 HNO2, 3 NO3. We have 6 electrons, and we would have 9 hydrogen ions. Okay, so at this point, we're now going to add these two together. So meaning, I'm going to take, just like in Hess's law, everything that's on the reactant side, we're going to write it in one reaction on the reactant side. So everything here, so our 14 hydrogen, our dichromate, our 6 electrons, 3 water, 3 HNO2, those are all going to be on the reactant side. And all of the products will be written on one product line. So let's take a look to see how that would appear. All right, so let's rewrite this all out. So we had 3 water, just to kind of squish this in here. 3HNO2 plus we had 14 hydrogens plus we have dichromate. Oof, that one. Let me write that out. Dichromate plus our 6 electrons. Okay, I'm going to put the product side just down here. So then we have 3NO3 plus 6 electrons plus 9 hydrogens plus 2 chromium ions plus 7 waters. Okay, so just for now, because we're just looking at this, we're not done yet. I just didn't write in the states just because we're not really. You're free to do this as well if you'd like. I do need to see the states in your final balanced equation though, okay? Just for, this is almost like rough work, right? Okay, so let's see if we can collect like terms or cancel whatever we can cancel. So we have 6 electrons on the left side. We have 6 electrons on the right side. Your electrons are gone, right? So remember, if you have the same substance on the left and right-hand side of the equation, you can cancel however many terms you possibly can. So we're going to see that right now with our waters, for example. So on the reactant side, we have 3 waters. On the product side, we have 7 waters. So these 3 waters can cancel, and we're left over with 4 on the product side. HNO2, we can't cancel. 14 hydrogens, though, we can cancel 9 of them because we have 9 hydrogens on the product side, which would leave us with 5 hydrogens. And then actually every other species here we would not cancel. So altogether our overall reaction is 3HNO2 plus 5 hydrogen ions plus our dichromate ions, making 3NO3. We have 2 chromiums plus 4 waters. Okay, so that's our overall balanced using the half reaction method, right? So if you were to go back and try out the oxidation number method, you should end up with the exact same answer. It's just an alternate way. Even though this appears to be more work, like there's more steps because you're writing out the half reactions first, I actually find sometimes students have an easier time with it because instead of looking at this whole thing all at once, you're breaking it up really into usually one thing on the left side, one thing on the right-hand side, and then you can just balance from there. There tends to be less errors. Even though it seems like there's more steps, there's less errors because you're looking at less numbers, I guess, at the beginning part of it. But regardless, both methods should work. Okay, so we're going to take a look at an example using a basic solution next.